Okay, so this one is definitely a less interesting background, and I thought about using a fake background, but I actually hate those things. This is taking place in our classroom. Um, since so many people were going to miss and we're almost out of time, I decided to go ahead and do a couple of videos. And by saying all that right now, it makes it where it's harder to use this video down the road. But sorry. Working on trying to kick a cold super fast. Anyway, this is for chapter 36, population ecology. It's going to go really quick. I'm going to do separate video lecture for chapters 37 and 38, solely so I can reuse them down the road, even if it is a really boring background. You know, I could always sit over there and have the windows behind me. Could make it really confusing and put something bizarre on the giant monitor and then turn where that's behind me. Nah, we'll just stick with this. So anyway, here we go. Chapter 36, population ecology. As usual, skip through the main ones. I'm going to recap. Not a whole lot of stuff here. So we talked previously about a population being a group of individuals of the same species. The example I used when I covered this in class last time was that anyone in this class is a population of Bio 124 students. That means you are in the same area, you have the same resources, you're influenced by all the same stuff. Likely to interact and breed with one another. Well, you're likely to interact with one another. I would prefer there be no breeding in the classroom. Population ecology is concerned with the changes in the size of the specific population. So they're going to be looking at if I kept going with this, retention rate of Bio 124 students, the pass-fail rate, that kind of thing. If we're doing it more like how population ecology really is done, I'm going to use like rabbits as an example. I once did an entire presentation, a thing about moving swamp rabbits into an area. So population ecology for the swamp rabbits would have to do with the swamp rabbits. Like how many moved into the area, how many left, how many are surviving, were there any diseases, that kind of a thing. I am so sorry. Population density. This is the number of individuals of a species per unit area volume. Basically, how dense is it? How many are crammed into the space? Different species require different amount of space around them. So like pandas, they like to be alone. So they need a whole huge range of the bamboo forest in order to survive. Okay, well, Ronald came in, so I don't know where I was, so I'm gonna have to actually edit this part. Um, so I will just say again that the population density is literally the number of individuals in that area. So the way that I tend to explain this is, I know I had started to say that about how a panda needs a lot of space and rabbits not as much space, you know? But sometimes it's hard for us to think about it. And so I point out, imagine living in a one-bedroom apartment and how many people you could handle having live in that apartment with you. Some cultures, as long as you had the floor space, you can pack them in. Other cultures, you're literally having one person. And so that's kind of how the population density works. Depends on the population to how many they can have in there. Dispersion pattern. So this is basically how it's dispersed. Now, a lot of times when we're talking about population, species, whatnot, we tend to just immediately think of animals. We forget about plants. We're going to be looking at plants for this stuff. We have the clumped dispersion pattern, and we have pictures coming up in just a moment. Uniform and random. So here you go. Clumped, perfect little clusters. So I would say these clumped are going to be like using humans. That's going to be like your suburban areas. Uniform, that's going to be your city. Because, city, we have the perfect blocks, unless, of course, you live in Atlanta. God knows they don't have perfect blocks, but most cities have blocks. So it's very uniform. Or even some of the subdivisions, very uniform. Clumped would be like, here's our little cluster of historic Norcross and our little cluster of Snellville. Random, this is going to be your rural areas. You can drive along and then there's a house and then there's nothing forever. And then there's a couple of houses and then there's nothing and then a house. So that's kind of how I see it. Life tables, I actually love these, but I don't make you do them. So this I get to go over pretty quick. And then the survivorship curves is basically to see how many are alive at the end of an age. So this is a life table. I would love to do a new one. This one clearly comes from 2011. And the way you read it is you see age interval and it says 0 through 10. So here you have 100,000 that you're starting with. And then the number that died between the ages of 0 and 10 was 770. This gives you a chance of survival rate of 99%. So 0.992 would be about 99%. So that means 99% chance of surviving past the age of 10. Now you take that new number, so that's 100,000 minus the 770 gives you 99,230. So for the age rate of 10 to 20, we have another 312 die. We still have a really high survival rate of 99.7%. You continue doing this as you go down, then you notice it's going to start to change around, well, I guess it changes mostly 50 to 60, but a big drop 60 to 70. This means from the age group of in your 60s, your survival rate is now about 88%. 70 to 80, 73.5%. 80 to 90, 41% chance of survival from 80 to 90. Notice the last one, 90 plus, is a 0% chance. That's because it's 90 until. You're not going to have anybody survive past the until because none of us are immortal. We have our survivorship curves. So we are type 1 is human, where relatively most likely to survive when we are children, and then we steadily drop off. As we get older, it gets more severe. Type 2 survivorship, kind of even all the way across. I mean, dude, I think it's perfect that they show squirrel here. We've seen what squirrels do. So they are constantly. And then they have like the oyster, the clams, the mussels, where a lot of their offspring die off right away. And then they just continue. So that's what that is. You do not need to know this equation, but basically it's the population growth rate equals the population size multiplied by the per capita rate of increase. That can be a positive or a negative. So if you have a lot of people being born, it's going to increase. If you have a lot of people immigrating into the area, well, not just people, but species coming in, then it's going to increase. If you have a lot of emigration, a lot of people leaving, a lot of species leaving, that's going to bring it down. If you have a lot of death, there you go. So here, exponential growth of rabbits. There's a reason they make comments about this. As long as they have the space, they're just going to keep on breeding. There's going to be more rabbits, upon more rabbits, upon more rabbits. Then we have our logistic growth model, which brings in the carrying capacity. Not really going to worry much about this one either. Just know that the carrying capacity is basically the cap. If you have too many there that the area cannot support them, they're going to die. That's just all there is to it. And this is showing you a population of seals and population explosion until there's just not enough space and resources, and then it balances out. All right, population density increases. The factors such as limited food supply and increased disease or predation may increase the death rate, decrease the birth rate, or both. So we have abiotic factors. Abiotic is in not living, density independent factors like weather. It's raining right now. When one of the students came in earlier this morning, like, is the rain ever going to stop? Things like this actually do affect the population. If it continues to rain, think about populations of, I don't know, like the ants that are outside. There's going to be a lot of flooding in some of their tunnels. We're going to lose some ants. So that's actually going to be a decrease until it dries out and allows them to start rebuilding. That can affect it. If it doesn't stop raining for days on end, you might remove an entire population. So that is an example of a density independent factor. A larger scale one would be things like Hurricane Helene, Milton, stuff that we've had previously. Not going to worry about that one or this one. Want to get to the more interesting ones here. Let's see. Boom bust cycles. I actually like these. These are where there is a poof, boom, like there is so much an increase in population, but then that caused such a stress on the population that bam, it immediately drops. This is what I wanted to get to. This is one of my favorites. Do I have a second slide of this? No, just that one. Okay, so population cycle of the snowshoe hare and the lynx. If you look, the black is the snowshoe hare, the red is the lynx. The snowshoe hare is the prey, the lynx is the predator. Every time you see a spike in the population for the snowshoe hare, notice after that you see a spike in the lynx population. You also see a poof, massive decline. This shows you the boom bust very well. Sometimes you can hypothesize that maybe the lynx had something to do with it, but in reality, it's probably more that there were just too many. But whenever there's too few snowshoe hares, then notice the lynx population also drops. This is a case where if there's too many snowshoe hares, like you see at that very top peak, they don't have enough food. There's going to be an increase of disease. Nature has a way of culling the herd. Then you have the predators who are munching on the prey. But then when there's not enough prey, the predators start to die off. And so it's this dynamic where one needs the other, which I don't know. I think it's kind of interesting. All right. Natural selection shapes species life history. This is not like, your personal biography. This is like how many are born, what happens during this age, the reproductive part, that kind of thing. So we have populations with our selected life history produce many offspring and grow very quickly in unpredictable environments. Think fish. That to me is the easiest one to think of, fish and insects. Populations that are K-selected traits raise few offspring and maintain relatively stable populations. And so that would be like us. A bear, that kind of thing. This is just showing you how it works with the population ecology for studying the various fish, and it shows the cycle. I'm not really worried about it. Then we have our sustainable resource management. This is where they are, well, first you have to remember sustainable. Sustainable means literally you are not taking more than you can replace. So it is not the idea of clear cutting a forest and then planting a bunch of baby trees, because that's not sustainable. It takes decades upon decades for the baby tree to become a large tree. And so a sustainable practice would be more like in stages. You cut this group of trees and then you plant a new batch of trees, but you have like 1 year, 2 year, 3 year, 4 year. You have all these different levels. So you're never completely running out. For fish, it's I want to say that I've covered this with you guys before, but I'm really not sure. So a sustainable resource management for fish would be like getting the fishing license, and they tell you that anything under this size, you throw back into the water. If you've ever wondered why that is, it all has to do with the reproduction of the fish. If it's too small, it's a baby fish. This might be a juvenile. It's almost a reproductive age. This one, reproductive. This is like the late teen, early 20s guy, very, very fertile. This is the one who's going to repopulate this ocean, or I mean, this lake, this pond, this river, this stream. This is grandpa. So grab grandpa. He's already done making new fish. He is not going to affect the sustainability of the population at all. This is also used when you get the bag limit or whatever for deer, and they tell you that there's no limit, or you can only do the 4-point buck or whatever. If they are not having enough deer in the area, then they're going to limit you to the oldest guys, which is going to be the one that has more points on his antlers. If they say no limit, that's because there's too many deer and they need to cull the herd. Because if you have too many deer, then you have an increase in disease. And believe it or not, deer can get very, very aggressive. And so these are the types of things that the sustainable resource management works with. Skip right on over that hatchery thing, but I kind of covered it. Now, for humans, population grew rapidly during the 20th century, and it stands now at more than 7 billion. That is insane. Demographic transition is a shift from high birth and death rates to low birth and death rates. And that has lowered the rate of growth in developed countries. What this means is while we have collectively gotten better with sanitation and medication and medical, we have slowed down the death rate, which means people live longer. In developed nations, you may have noticed a lot of people don't have as many kids. So that slows the birth rate. If we are slowing the birth rate, then that is keeping us from getting way overpopulated. In developing nations, the death rates have dropped, but the birth rates are still high. So they tend to have a problem of too many people being born, not enough resources. Age structure of a population is the proportion of individuals in the different age groups. And this affects the future growth. And we've got some charts coming on this in a second. Population momentum, continued growth rate that occurs despite the reduction of the fertility rate. So result of girls in the 0 to 14 age group of a previously expanding population reaching their childbearing years. So even if you have stopped having kids for a period of time, the ones you did have are eventually going to reach maturity and then have kids of their own. And that's what this shows you. So here we are looking at that one little section that is marked off in, what is that, yellowish orange? It shows you here that a lot of babies were born. When they get to reproductive age, they have more babies. And then you notice the green is going to be the babies that the orangish gave. And then as they get older, and if you notice up at the top, you didn't have a whole lot of old people, but now suddenly you're getting way more. This is one of those things. It's not just about the population itself. It's also the age categories. Because now if you have this next group having fewer kids, the ones who are there ahead are still going to get older, and you may end up with a huge older population and not enough people to take care of them. And so this is the stuff that a lot of the census looks at and a lot of cultures look at. And China, a long time ago, realized they had way too many people, so they implemented the one-child program. It was not where they were killing off the one kid. It was not technically illegal. It was just you were going to be looked down upon because you would be showing that you cared more about yourself than your country. And that was a big thing. But it worked very well at bringing down the population to where now China has been realizing that they don't have enough people to fill all the spots, to take care of everybody. And so now they're going practically door to door asking, why are you not having children? And they're trying to push more increase of children, which is interesting. The US is doing something similar right now too, but we're not getting into that right now. All right, age structure diagrams reveal a population's growth trends and social conditions. I kind of already covered this. So like if you have a whole bunch of young kids, you're going to need more schools. If you have a large elderly population, you're going to need to have a lot more healthcare. This is literally what our census is for. How large a population of humans can Earth hold? Well, if we took better care of our planet, it would be okay. The issue is we don't. We are very wasteful. And so that brings up the ecological footprint. This estimates the amount of land required by each person or country to produce all the resources it consumes and absorb all its wastes. We are not doing well on this one. So you compare your demand for resources with biocapacity, again, life capacity, so how much we can hold life. And we find out that a lot of what we do is destroying things. So this is old school. Some of this has changed. What they're showing here is the green footprints are per person, how much we waste, or what size of an ecological footprint we do. And then the blue is as a nation. So take a look at Australia, where you're like, oh my gosh, that's huge for the individual, but for a nation, it's tiny. The United States, oh no, we're pretty big in both. China's pretty big in both. And so it's not surprising that the US and China, we're the big ones. We are very wasteful. We are destroying a lot, which of course I covered environmental science. Sustainability, goodness gracious, I have talked about this ad nauseum. Hopefully you already know the entire purpose of sustainability is to actually not use more than you can replace, because it's not just about you, it's about all of the future. It's, I think that's one of the biggest issues I have with a lot of people who don't want to adjust anything is they have a tendency to be very self-centered and not think about future generations. I desperately want grandkids, and I want those grandkids to have kids, and I want those great grandkids to have kids. I want all of my future descendants to still be able to breathe when they go outside. I want them to still see waterfalls and green and nature and hear the animals. I want them to be able to go into a rainforest and see the beauty that I see there. So I make a lot of my decisions on what I want my future descendants to see. And that is the whole goal of sustainability, is making sure that future generations still have what they need. So this would be the equivalent of, oh my gosh, trying to remember the exact phrasing. There is this exercise where they show people like at a work function, and then there's the pizza party. You've got the pizzas laid out there, and they tell you that there is enough for everybody if everybody only takes their share. And you've got the people who go through there and they grab a little bit extra because they might want a little bit more afterwards, and there might not be any left for the people at the back of the line. Then you have people who go through the line who take less than their share for exactly the same purpose, knowing there might not be enough for the people at the back of the line. This idea of sustainability is literally that. Do you take extra so you have everything you want and chance the people at the end of the line not having anything? Or do you try to take less than you actually want to make sure that the people at the end still have what they need? That's pretty much it. And that is the end of this chapter. So, guess that's it. Peace out.